I want to talk about how do we accelerate innovation? How do we go beyond what we have achieved so far in the machine learning space, which is developing rapidly, and what are some of the problems we need to face? What are some of the problems we need to solve before we're there? I don't know if you know Tim Urban and his Wait But Why. I really encourage you to read that. I love his graphs. Basically, if you look at exponential growth, it is a funny beast. Exponential growth means that looking back, you're always seeing a pretty linear thing. It's like, yeah, it's been great, but could be better. But if you only turn around, you'll see this wall of skyrocketing stuff. And machine learning looks like that. Machine learning has been growing very fast, but we can only expect it to grow even faster in an exponential way. Google actually predicts that it's only 2 years before the needs and the ambitions and the hunger for machine learning exceed our compute capacity, and so, we've lost. We've run out of compute capacity. We cannot do as ambitious machine learning as we would like to do. So what's the answer? Google has been trying to fix that problem with the TPU. They identified the problem. They saw, OK, we need more compute. And they wanted to keep up with this instant growth in software and algorithms. So they built the TPU because they estimated without it, they wouldn't be able to provide the level of support for all those audio-based services like Google Duplex or Google Assistant to people worldwide. If you're building things in a lab, you can get access to whatever compute capability you want, but once you scale it up to everyone, it becomes a huge problem. So without the TPU, Google wouldn't have cut it. And from their estimations, well, it only took 1.5 years to create and deploy this system in data centers worldwide. That's really impressive. That is a very fast pace. But is it really enough? Well, if you look at my last slide and me saying that we're 2 years away from the end, then obviously it's not. Obviously, we're here in the RISC-V summit trying to figure out this very thing. We are here to say, look, let's try to make ASICs faster and more free. Let's try to solve this challenge. And of course, the open ISA that we have is allowing us a lot of freedom in the core part of our ASIC designs. And companies like SiFi are allowing people to build chips faster, so they decrease the turnaround time and hope that we can just accelerate in a better way. But again, is this enough? Well, as you probably think, you know the answer. 2 years away from the end, so probably no. Well, the challenges are that if we go beyond the CPU, the non-CPU stuff is still hard. The supply chains, building chips, this is still a quite difficult problem. We don't have enough Linux-enabled cores, so we can't tap into the broad Linux ecosystem so well as we would want to do. And, well, developers are here. We're definitely in much bigger numbers than we used to be. It's a great success, but compared to the wide software development ecosystem, I think there's still lots of work to do. So we're on the right path, but we're just going too slow. The Linux analogy for RISC-V that Kirsta has been making all the time, I really like, because I believe it's pretty true. Although if we think about RISC-V as Linux, we will actually need more. We'll need the GNUs and the Apaches and the Kubernetes, the Dockers, Cafes, TensorFlows, all the things that actually make Linux a fun thing. Linux on its own is not enough. So if we say that the ISA is the language of the computer that it speaks, well, we have a language. It's a great language. It's a very mature language, and we can speak it. But we actually need to write our books and build our libraries. If we take a comparison to the software world and the world of machine learning, if we look at Google's TensorFlow, even though Google is the leader in the AI space and they've been really successful in solving lots of hard problems, they still think that they need help of the broad development community to actually pull this off. They have open source TensorFlow, which is a crown jewel of their machine learning ecosystem, and they're building cheap AIY kits to have people develop things for TensorFlow. They give free courses, they build massive conferences, all in the hope that they can outpace this demand that's going to hit us in 2 years. So they need the community. They need the community to build the demos, to contribute non-trivial use cases, and expand the ecosystem in ways that Google couldn't imagine themselves. And I think we need to do the same. So how can we do this? How can we get the speed of software in RISC-V and in the hardware community? Definitely, one problem that we're facing is that however much we increase the turnaround of building chips, what software people want is instant. They want to just build stuff and test it immediately. They don't want to wait. Another thing is, if we only build the cores, well, obviously, that's not the only thing the software needs. There's a lot of IP that goes into building an actual chip. And also, if we can build this chip for $100,000, which is great, which is like a great revolution from before when it cost millions, $100,000 is not exactly the amount of money that a hobbyist out there will spend on doing his hobby project. Also, if our major development platform is a $1,000 board, it's also a barrier of entry that is not possible to pass by many people out there. So we need to do better. Where do we turn to get this instant turnaround? What do we do to get this accessibility that I'm talking of? The answer is FPGA. I know, of course, that we've been using FPGAs, and everyone here is probably at least a little bit acquainted with this concept. But if we look at it more closely, if we reevaluate what we know about FPGAs, we can figure out that there's actually lots of potential in there. It is like a flexible chip. You could use it to build ASIC-like stuff. It is slower, of course, as everyone will be very keen to point out. But you can actually write code, deploy stuff, and test it, and turnaround is very, very quick. At least decent as compared to software. Software people will always complain, of course. If you have bugs, well, just fix them. Recompile the bit stream, upload it again, done. It's not like ASICs, right? The entry barriers are there, but they're quite bearable. The hardware, well, it exists. It's not super cheap, but it's definitely reachable. So if we talk to software people about FPGAs and we introduce this concept in the right way, if we convince them that the barriers are not that bad, typically what they say is, wow, this is great. I didn't know I could do hardware. This is really cool. So there's hope. So if we look at FPGAs as a kind of a bridge between the software world and the hardware world, I think it's a pretty interesting way to view them, and I think that we've been doing too little of that. So I deliberately, of course, used the bridge, you all know, because we're here in the Bay Area. And I think that's a very important role for FPGAs to play, and I think we should look at them more closely. Of course, FPGAs are not just a bridge, right? They are actually very useful as flexible interconnect and I/O for other kinds of chips, especially heterogeneous platforms. They're very adaptable, so there are some machine learning tasks that are actually quite, where FPGAs are quite useful because you can reprogram them on the fly in the field and get some new capabilities. And so we believe that as we go forward, the capabilities of FPGAs and the possibilities offered by them are going to be very important. Now, it's not all fun and games. FPGAs have their own problems. They're a quite niche technology. And I used a lot of bearable and decent and fairly in the previous slides because, of course, all these things come with a little asterisk. If you compare FPGAs to software, the software people always say, oh my god, I don't want to do this because I'm used to just doing git pull and compiling and done. But, the tools and methodologies that we have for FPGA are also a problem. But actually, these are all solvable problems. We can do a lot to popularize this technology, to build up the community, to enhance and tend for the open source IPs out there and build practical things out of them. And we can acknowledge the important role that FPGAs play. And if we do that, if we can actually bridge between hardware and software, what we'll gain is an incredible amount of energy, an incredible amount of people, developers that could contribute to hardware development. They would never go and build an ASIC. They don't have the capability, the time, the money to do that. But they could actually do FPGA. And I think that it only makes sense if we do it in an open source way. All of this only matters if we do a lot of open source approach in FPGAs, because that's the only thing that the software people will care about. And the collaboration, the cross-development, and the spontaneous innovation that you can get from it are really unprecedented, and I'll tell you about a few of these things later. As I was saying, the cores are very, very important, but I think we're slowly getting this sorted here in this community. But if you go beyond the core, that's what you need to do to get more people involved, because to do practical things, you will need also IOs and other kinds of IPs to make something practical. So what Antmicro has been trying to do was to foster ecosystems of IPs and reference designs that could help build practical stuff by lots of people out there. One of the projects we've been involved with that has been kind of part of this summit is 32-bit open Linux-enabled system on chip based on Lite and Vectors 5. It is a soft core and a bundle of IPs that allow you to run Linux in an FPGA. We deliberately chose a low-cost development board from Microsemi, the PolarFire, well, actually from Future Electronics, but within a Microsemi and FPGA. What's important in this project is that we're trying to make the RISC-V Linux more well-suited to FPGA development for soft CPUs. We want to enable low-cost development platforms that don't cost $1,000. This is only $180 for people that would like to try out RISC-V, but they're not going to tape out a chip. And perhaps they've done some simulation work, but they might want to do something more. And FPGAs are a way to experience RISC-V in a more practical context. Another project we've been involved with that we're very happy has been actually open sourced last week was a project with Thales for whom we'd built a triple modular redundancy system. And this system has come about in something like 6 months as compared to probably years of work that would have gone into it if we had to design all the things that go into it from scratch. But we were able to build on an ecosystem of cores and software. There's a lot of elements like Zephyr and Chisel and the rocket chip that we could leverage here that we just got for free, right? And then, of course, we still had a lot of work in front of us, but that work was constrained to the stuff that really mattered. And I think that's what software people want to hear. OK, most of the stuff is done. I just need to kind of build on top of that. That's how they're used to work. So we've been able to successfully build this in a very quick, short time, and Thales has open sourced it, and they're going to be able to tap into wider community of developers to help them build out from this into new use cases, new applications. This is quite unique for a company this size and living in the space that they're living. So I think it's a really big success that this is now open source, and I encourage you, of course, to look it up and try it out. So apart from the broader IP ecosystem, that of course also some of the announcements you've heard over the last 2 days have been talking about Western Digital with their interconnect and other people. These things certainly help. But we also need new platforms and new tools and methodologies to more effectively work with open hardware and FPGAs. One such platform I think that's going to play a very key role is the one that's been announced by Microchip or Microsemi, their subsidiary, is the PolarFire SoC. That's FPGA system on chip based on RISC-V. Now, FPGA system on chips have actually been instrumental in building out the broad open hardware community. If you remember Parallella, if you remember other projects in the hardware domain, they've been using FPGA SoCs to bridge between software and hardware. So having a RISC-V based FPGA SoC where you can use a hard RISC-V core to run pretty ambitious software and then accelerate your software with an FPGA and add new IPs and flexible IOs in this FPGA, I think this is going to be a huge step forward for RISC-V. So I'm very excited for this announcement. And I'm all the more excited because actually we've been able to innovate also on the tools and development methodologies front here. As you know, there is this excellent kit that you can develop for PolarFire SoC. The only problem with it is that it barely fits into my slide, And it also barely fits into luggage if you want to carry it around, and it costs $300. It's not exactly something a software person would normally grab and do stuff on. On top of that, what we're proposing and what we've been working with Microsemi to build is a simulation framework that can take the entire PolarFire SoC and make it available to everyone out there, for people to do hardware-software co-development, for people to do early pre-silicon development for PFSoC, and that is Renode. That is the open source simulation framework that Micro is developing. And already now, you can go to GitHub, you can download version 1.6, and you can start developing things for PolarFire SoC. So I also encourage you to start doing that. And what we're trying to pull off here is not just replacing the silicon before it's available. That would be, great, but not really what we are looking for. What we're looking for is enabling a more continuous integration-based workflow for everyone so that using a simulator, they can start building and testing their system before it's even shipped. And once it ships, they can still continue using the same methodology, they can continue using the same workflow that they were used to, because Renode allows you to do that. It's binary compatible with the hardware, so you'll be able to use the same production firmware and software for both the physical and the software platform. Another aspect of tooling that we've been looking into at Antmicro is, for example, how do you enable standardized tools that people can just grab and start using in the RISC-V context. And we've been working with the Google team on TensorFlow, and they have actually been using Renode to test TensorFlow Lite on microcontrollers so that they can make sure that their machine learning framework doesn't just deteriorate over time, doesn't get buggy. Because if we want to accelerate, if we want to go faster, if we want to build things on top of other things, we cannot really afford bugs. And TensorFlow Lite, we started off with an ARM-based platform, but actually what we've been able to do right before this summit is to enable TensorFlow Lite on RISC-V. And all that development work was done with Renode, and only then actually we implemented that in the hardware, and guess what? It worked. So the last thing I want to talk about is how do we reach out to the broader community to go beyond the SA and tap into the energy that exists in other places. First of all, we are trying to call into action a RISC-V SoftCPU task group. We have a lot of interested parties right now. You can see them on the screen. I'm pretty sure a lot of you will be interested to join that group. What we want to do is to encourage RISC-V as a viable choice for FPGAs. We want to make sure that it remains an ISA that matters to people that want to do FPGAs. We want to make sure that it's well adapted to this, all this I was talking about before, that people can just grab it and start developing RISC-V on an FPGA board. We also want to reach out to the broader IP ecosystem and, generally speaking, make sure that anything we do corresponds to what's needed out there and what people actually think matters. So all the partners listed here are already on board, but of course you can come talk to us and join. We highly encourage you to do that. The contest is also another thing through which we were trying to spark some innovation in the FPGA space. So we told people that they can develop a soft CPU that might be either very small or very performant or otherwise innovative. And we'll be giving away prizes for this so that people actually care about doing these things. And it turns out that we had really good results. Rick is going to say more about this. But I'm very excited that even though it was just the first edition, so we had a lot to learn, and I'm sure if we do next editions, it's going to be even better. There's still a very good output. There's still a lot of creativity we had. So I think it's a very simple way to get people to do great things, and Rick will tell you more about this in a second. We'll also be having a workshop that's primarily being driven by Symbiotic EDA. It's called the Date OSDA workshop for open source design automation for FPGAs. We highly encourage you to join it and listen. There's a lot of exciting stuff happening in design automation space, also for FPGAs. So I think that it's a very important event that you shouldn't miss. The last thing I wanted to mention is that we're actively working with the EU to make open hardware a priority for the European Union. We were working with Thales to put a lot of good content into this agenda to make sure that it really focuses on open hardware, because we believe it is the way forward. And what the agenda actually reads in many places is very aligned with what the RISC-V Foundation is trying to pull off. So it's actually saying that using the RISC-V ISA, Europe can be a leader in this space. And of course, we have other people doing similar things in India and China and other regions of the world. We think these activities are really key to make people aware that there's important people caring about open hardware. You're not anymore in a niche. You're not anymore just on your own doing some kind of a hobbyist project. You are actually driven by strategic agendas around the world. So summing up, What I was talking about here was a couple of elements that we need to make stuff happen. All of this is driven by a real need coming from machine learning that is just pushing our compute needs to the sky. And we think FPGAs and open source are central to this effort. And Micro, together with a host of partners, we're trying to push this wide ecosystem and build reference IPs and development platforms and tools for the software people to care, for the broad community to really pick up RISC-V and start doing things. We encourage you to collaborate with us on those goals. We don't think these are just, some random small things that are interesting but otherwise not useful. We think it's essential to the future of machine learning at large. If we don't do this, if we actually just stop at, okay, let's continue developing great cores and that's it, we think we'll, of course, have some kind of progress, but it's not going to be the progress that allows us to face that wall that we're actually going very fast towards. Remember, 2 years. We have 2 years to fix things. So we have to act on multiple fronts, and that's what I'm calling you out to do. Thank you very much.